Thanks for having me. So I want to tell you a little bit about what we're doing to modernize the Cadence scheduling for the Keck Planet Finder, but I hope there's many synergies with other facilities. So the importance of Cadence needs very little motivation for this audience, but just to say in a sentence, appropriate sampling is critical to both detect and disentangle planetary and stellar activity signatures, which have timescales ranging from minutes to decades. So in this talk, I want to describe some of the current limitations of what we're doing at Keck, introduce community cadence, which is an efficient and equitable queue for PRV science, and describe a prototype framework that we already developed for Keck high-res that uses something called integer linear optimization. So one of the main challenges of doing PRV science at Keck Observatory is that it's a classical observatory. So what happens is that PIs are typically awarded time in integer numbers of nights, ranging from 1 to 10 nights for a large program. And that's not well suited to PRV science, which requires small samples of time on many nights. So we've been chugging along sort of with this backdoor workaround, which is to run an ad hoc queue by an organization called the California Planet Search, led by Andrew Howard. And what happens is that a number of science PIs elect to collaborate with CPS, and they propose for time through a number of tacks. The successful proposals get rolled up and sent off to Carolyn Jordan, who's the Keck scheduler, and she produces a semester schedule for the whole telescope. Very little cadence information goes into the creation of this schedule. It's basically just things like target coordinates. Then Howard Isaacson, who's the chief CPS scheduler, looks at the schedule and solicits cadence requests from our CPS collaborators. And Howard has the arduous task of coming up with observing scripts for each night, which are executed by a pool of trained observers. And I say this is arduous because we typically execute up to 3,000 exposures per semester. And so there's 3,000 factorial possible schedules. So this is a really highly complex problem. Okay, so this has worked well for a while, but we're really reaching the limitations of this arrangement. One of the issues is that KPF will be at a telescope that's highly competitive, and it's never going to be a PRV only instrument. So even under very RV heavy semesters where we have roughly a quarter of all Keck 1 time, high-res has only been on Sky for roughly a third of all nights. And we know that many PRV programs benefit from nightly or near nightly coverage. In addition, PIs that want to do PRV science with high-res are forced to collaborate with a certain research group, which they may not want to do. And this is poor policy for NASA, which is trying to create an open access facility. And then finally, this is just a lot of work for CPS. We've basically never had this effort funded, and it accounts for about a cumulative of about 1 FTE of effort. So here's what we're going for. So it's a new program called KPF Community Cadence. And what it is an opt-in PRV queue at Keck. So our main science goals are enabling optimal sampling of planetary and stellar activity signatures. Our goal is to get KPF on Sky most nights. 75% would be ideal. And this is going to be done mostly through quarter nights. And we want to provide equitable access for both large and small programs. Now, one of the practical requirements is that we need this to be automated. Keck has no funds to support a dedicated Doppler cadence queue scheduler. So what we've done is we've surveyed the landscape of automated telescope scheduling. And I should say that most telescopes are still scheduled today by hand, but there are a number of groups that have worked on automated approaches. I don't have time to get into all of these different approaches. They're quite different. I'll just say that we've settled on a technique called constrained integer linear optimization. And this is what's employed by the LCO network as well as the Zwicky transient facility. One of the things that's very appealing about this method is that it's used throughout the business logistics community to solve very similar problems. So for example, when the NFL, the National Football League, puts together a schedule, they're trying to maximize profit, of course, subject to a number of constraints. And so these are things like home and away balance, player fatigue, broadcasting rights, many more. And they in fact analyze about 1 trillion possible schedules. And this is done efficiently using commercial optimizers that have been used to solve problems like this. And Gurobi, I think, is the industry leader there. And this is similar to the challenge of scheduling RV observations throughout a semester. Another related problem is the vehicle routing problem with time windows. And so, when FedEx wants to distribute packages to a bunch of customers, a bunch of recipients within certain time windows, they need to figure out how to do this with the least amount of miles on their trucks. And this is similar to constructing a star list where the whole sky is moving above your telescope. Okay, so what is constrained linear optimization? It's basically optimizing a linear objective function of many variables, and it's bounded by constraints, which in 2 dimensions are just lines in a plane. So if it wasn't for these constraints, the objective function would just increase monotonically ad infinitum, but these constraints bound the problem. And so the goal is to just find the vertex that optimizes this objective function. And in reality, what we want to do is find the integer solution, and that actually makes the problem quite a bit harder. So you can think about a telescope schedule as a matrix that has targets on the rows and slots on the columns. And the scheduling problem is just slotting those observations into slotting those targets into the various slots. So we can represent a scheduled target with a 1 if target T is scheduled into slot S. And the values of this Y matrix that are 1 are just the set of all scheduled observations. So I'm going to start off with a trivial example and build our way up to a real schedule. So you can imagine a trivial example where you're trying to schedule 2 targets into 2 slots. Target 1 is only up during slot 1, target 2 is only up during slot 2, and of course you can only observe 1 target at a time. So you can solve this problem by maximizing just the number of scheduled observations subject to those constraints, and that's equivalent to choosing those Y variables subject to a system of 6 constraints. So you can do that, you get the obvious answer, which is this schedule over here. It's a bit like using a machine gun to kill a mosquito, but this is a technique that can be extended to much more complicated scheduling problems. Okay, so working our way up, you could imagine a toy 30-day semester where you have 3 programs, each that have been awarded the same amount of total time, but they're burning their time in different ways. So program 1 might be a high cadence program where they're trying to observe a single target every night. Program 2 could be a medium cadence program where you're observing 3 targets 3 nights. And program 3 would be a low cadence program where you're observing 10 targets every 10 nights. So the same amount of total time. Cast in the mathematical framework of constrained integer linear optimization, this corresponds to 6,000 constraints and about 10,000 variables. But this can be solved very quickly in about 2 seconds on a laptop. And what you can see here is that the schedule that Gurobi returns is exactly what we want, right? We want this red observation every night, the blue observation every 3 nights, and the orange observation every 10 nights. So this is behaving just as we'd like, and there are no gaps in the schedule over here. So we've perfectly filled the schedule. So what we've done is we've deployed this already at high res. And I really want to acknowledge the work of Luke Hanley, a UCLA undergrad who built this code. And what we do is we're trying to balance the needs of about 10 programs, a total of 400 targets, and roughly 1,000 or so observations. And these are allocated into about 80 quarter nights. So the science PIs provide the targets, coordinates, estimated exposure times, and then critically the cadence. So this is a multi-step process. Step 1 is to assign all of the observations into quarter nights. And this amounts to finding the optimal set of about 30,000 decision variables subject to 50,000 constraints that specify the cadence. And this problem can be solved in about 2 minutes on a laptop. Just to give you an example of one program, this is the Distant Giants survey. This is one of the programs we're executing with high res. This is led by Judah Van Zandt. And the idea here is to observe 50 test planet hosting targets roughly every month. And so this is just a few of them. The black lines show the scheduled observations. The green bands show the visibility windows. And you can see that we're getting regular cadence. So this is great. We can even project, we can forecast the completion rate of TKS distant giants. And because the whole Keck schedule isn't designed with cadence constraints in mind, we actually know that we're not even going to be able to finish, all of the desired observations. So sorry, Judah. And we can do this for all of the programs that we're looking at. And so we can look at the cumulative completion rate as a function of day in the semester. Some programs are doing better than others, but this difference, this gap between what we want and what we're going to get is due to this mismatch in how the Keck block schedule is created. So that's scheduling into quarter nights. And then step 2 is just optimizing for telescope slew. So this is a time-dependent traveling salesman problem. It has a different interlinear optimization, but Luke's figured out how to do this. And so what I'm showing with these videos over here is just an optimal slew schedule that's all determined automatically versus a random one. And you can see down here that for one, we spend about 8 minutes total slewing. The other one, we spend about 20 minutes. So you can slot in a few extra observations if you do things optimally. So with this auto scheduler with high-res, we've changed our model a little bit. So the science PIs communicate their cadence requests to Luke, who runs the auto scheduler, produces a draft script. Howard still looks it over, but now the auto scheduler is good enough that it needs sometimes no modification at all. And then the final scripts are still executed by human observers. So I'll put my summary up here. We're working toward an optimal, automatic, and equitable scheduling system for KPF at Keck. We've deployed a prototype of this at Keck High-Res, and I'm looking forward to doing this for real with KPF. So thank you.
Yeah, Andreas.
Thank you. Hey, Erik. Do you ask your PIs for a minimum completion rate, so to speak, to make a program viable? Making this hard decision maybe in the middle of a semester to say, okay, projected, we will never reach, 30, 40% or whatever, and that's not really useful for that program. Let's rather complete other programs and abandon one.
So we don't do this yet in the auto scheduling approach. We rely on sort of our experience as RV observers ourselves to sort of notify PIs when, say, you're only going to get a few RVs on a certain target. It's probably best to just bag that one and invest that time somewhere else. So the code doesn't have the ability to do that yet. So this is the type of thing that we'd love to build in. And don't know exactly how you do that, but it's definitely something that we should.
This looks like a huge amount of work to kind of work your way around a facility problem. But my real question is, how does this handle, or does it handle changes within a night? Because you can have a nightly schedule that's set with all of the great intention of the world, and then a cloud comes through and wipes out your observation that you planned for 11:04. And then are you adaptive, or are you planning to be adaptive to then adjust the rest of the night accordingly?
Yeah, so this is actually not that different from the way that other large Q-based observatories work. So for example, Gemini, every night they'll put together something like 10 schedules for different seeing and transmission bands. And then as the telescope goes between those different observing conditions, they'll jump between one script and another. So you could imagine this algorithm pre-computing a number of scripts for different conditions. But one of our practical requirements that we're trying to meet is that this thing needs to be able to run in quasi-real time. So that's why I mentioned that both of these steps take a few minutes to optimize. We don't want to get much more above that. And that way we can adaptively respond to changes in weather. So 2 minutes on a laptop is pretty good. If it gets more complicated, we could use a heavier duty machine.
One last question.
Hi, Erik, great talk. Just quick question. So in your objective function, you take only into account the constraints which have been given by the observers, and so you don't try to optimize for a particular science goal, a particular type of observation.
Yes. Yeah. Okay. So that's a good point. The objective function is trying to maximize the completion rate of all programs. So we let the PIs figure out whether or not that's scientifically viable, and that's the Keck model. We're not going to favor one successful proposal over another. Those have to be treated equally. But it's just completion rate.
Thanks.
All right, let's thank Erik and the